Hi students, this video covers section 4.5, modeling with exponential and logarithmic functions. This particular video will cover slides 1 through 8, PowerPoint slides 1 through 8. So we're going to be concerning ourselves with making a mathematical model. For us, a mathematical model is going to be a formula used to describe quantities in the real world. And in particular, we're going to be looking at exponential growth and also exponential decay models. And those models have a particular format. And here you see the format is A is equal to A sub 0 e to the kt, where in this formula, A represents the amount, T represents the time, usually in years. K represents the growth rate, and A sub 0 represents the original amount, the original quantity. So that's the amount at time t equals 0, so you can think of that as the time when the clock is turned on. We have exponential growth models. And if you have a growth model, the value of k, the constant, is positive. So if you have exponential growth, you'll have an initial amount that's represented by A sub 0 and is the y-intercept here. And as time advances, the amount gets larger and larger and larger and increases without bound. So when k is greater than 0, we have exponential growth. If k is less than 0, we have what's called exponential decay. So a decay model has a graph that looks like this. And so what you'll have is you'll have an initial amount represented by A sub 0. And as time advances, the amount of the quantity that you're studying gets smaller and smaller as time advances. So it gets smaller and smaller, and it decays and gets slower and closer to 0. So what I want to do is to look at a particular problem that will involve specifically exponential growth. In particular, we're going to look at making a exponential growth model. So here's the checkpoint problem. They say in 1990, the population of Africa was 643 million. And by 2006, it had grown to 906 million. The question has two parts. The first part says, use the exponential growth model, and then they give you the formula, in which t is the number of years after 1990 to find the exponential growth function that models the data. So the problem is asking us to come up with a function. So a function is a formula. So we don't expect the answer to be a number. We expect the answer to be an equation with variables in it. And then part B says, by which year will Africa's population reach 2,000 million or 2 billion? So once we have our formula, what we're going to be able to do is to answer the second part of this question. That is, in which year will Africa's population reach 2 billion? So let's start the problem. So again, we have our basic formula. So A is equal to A sub 0 e to the kt, where the variables in the formula represent the following quantities. So A represents the population at any time t. A sub 0 represents the population in millions in 1990. So that's the initial size of the population. So that's the time at which we start looking at the size of the population. And so t represents the time in years since 1990. So if t is equal to 0, that corresponds to the year 1990. If t is equal to 1, that corresponds to the year 1991. If t is equal to 2, that corresponds to 1992. And if t equals 16, that corresponds to 2006. So you can get a value of t equals 16 by doing the following. Just do the following subtraction. If you take 2006 minus 1990, the difference there will be 16, and so that represents the appropriate t value. So t equals 16 corresponds to 2006. So what I'd just like to do is to put the information in a table, so I know that at t equals 0, we have, and the amount is in millions, we have a population of 643 million. And so that means that a sub 0, that is the initial population, is 643 million, or represented here by 643. And so if our basic formula is a is equal to a sub 0 e to the kt, then that means that our basic function will have the format a is equal to 643 e to the kt. So what we need to do in order to find our growth function is, at this point, we need to find the value of k. So that's where we stand now. We want to find the value of k. So in order to find the value of k, we use the fact that we know the size of the population in 2006. That is, in 2006, which corresponds to a t-value of 16, we know the size of the population is 906 million. So what we need to do is we need to set a equal to 906, and we set t because we know that that corresponds, 2006 corresponds to a t value of 16. So we put those two values in our basic formula, and so we have what you see here. 906 is equal to 643 e raised to the 16k power. So now we have an exponential equation. So recall, exponential equations have a number raised to a variable power. So here our variable power is k. And so that's how you recognize exponential equations. And so typically you want to solve exponential equations by isolating the exponential expression. So here that's e raised to the 16k, but you'll notice that 643 is multiplied to it. So what you want to do is to divide both sides of the equation by 643. So that's what's done, and so now we have this fraction is equal to our exponential equation. Now we have an exponential equation. Now the problem with exponential equations is that the variable is in an inconvenient place. It's up there where the exponents are. So to move the position of the exponents, we're going to have to introduce our log function, in particular our natural log function, and then apply its power rule. So I'm going to use the fact that if two numbers are equal, if you substitute those numbers into the same natural log function, the results will be equal. So here I do that here, and so here you have the corresponding equation. So this is natural log of 906 divided by 643 is equal to the natural log of e raised to the 16k power. So now by the power rule, we know that exponents become coefficients, and so what we'll do is we'll move the position of that exponent to 16k, and then we'll multiply it by the natural log that is left behind once that exponent is moved. So this is 16k times the natural log of e, and so the natural log of e turns out to be 1. Recall that if you're calculating the natural log of e, it's log base e of 1, log base e of e. So you're asking e to what power makes e, and of course the answer is 1. So that's why we replace the natural log of e with 1. So now we have our natural log of 906 divided by 643 is equal to 16k. So the next thing we want to do is to solve for k. So that means that since we have an equation of number times letter is equal to number, we just divide both sides of the equation by 16. So now we have k is equal to the fraction that you see here. We put those values in our calculator, and we end up with this rather long decimal number. So k is equal to 0.02143091114. So I go back to my formula that I have. It's A is equal to 643 e to the kt. And what I decided to do was to approximate the value of k to 4 decimal places, 4 significant digits. And so now I have my exponential growth function. So my exponential growth function A is approximately equal to 643 e raised to the 0.02143 t power. So we have the first part of the question answered. Now we have to address the second part, because now we have the exponential growth function. Now we want to address the second part. So the second part of the question is this: find the year. So here we want to find the year when the population is 2,000 million or 2 billion. So in order to answer that question, we set A equal to 2,000 and we solve for t. So we know the population is in millions, and so 2 billion corresponds to 2,000 million. That's why we set A equal to 2,000. But we don't know when the population will reach that value. So that's why we have to solve for t. So substituting 2,000 in place of A, we end up with the equation that you see here. So this is 2,000 is equal to 643 e raised to the 0.02143 t power. And so again, we end up with an exponential equation that we want to solve. So now we divide both sides of the equation by 643, so we end up with this fraction. We apply the natural log to both sides using the idea that if two numbers are equal, if you substitute those numbers into the same natural log, the results are equal. Then we apply the power rule, and then the resulting equation becomes what you see there. So this is 0.02143t. So now we solve for t. So when we solve for t, we end up with the natural log of 2,000 divided by 643 divided by 0.02143. And so we put that value in our calculator and we get t is approximately 53. Now that's not saying that the population will reach 2 billion in the year 53. Remember, t was the time since 1990. So to figure out the year, what we need to do is we need to add 53 to 1990 to get the year. And so when you add 53 to 1990, you end up with the year 2043. So now we can answer part B. That is, in 2003, the population will be 2 billion.